So in the meantime, we're going to move on to our second presenter for this afternoon. And this time you do actually get to hear from the real Mike Whitbread. Mike is a geochemist with over 25 years of applied experience in the exploration and mining industry. He currently works for Rio Tinto Exploration, which is, I think came through during the Dennis impersonation. And his talk today is entitled QC Life Rafts in the Age of Assay Data Tsunamis. So we will get the pleasure of trying to work out what actually that means.
Yeah, that's a bit of a marketing exercise, really, that one. But so this talk, I've got to be 20 minutes ahead of myself now. This talk was put together in 2020, right? So none of these slides have changed. So some of what we're doing will be quite different from what you're seeing here. The process of getting approvals for slides in large companies, for those who are a part of that, it's better to not rock the boat and just keep going. But anyway, it's good to have the opportunity to come and talk to you about an experience that we had when we discovered Winu. So we've done some other talks in the space around this deposit. One is around what we're using the assay data for, like automatically predicting lithology and things like that, using machine learning and a few other cool things. And I think there's been some presentations from the geoscientists about how the deposit formed. We're not going to talk about any of that today. I'm going to talk about what happened when we discovered the deposit and then we got told to move it very quickly, right? And everything went berserk. It's probably not the appropriate word to use, but see if we can. Sorry. Okay, over here. Right. Okay, we're good. So hopefully you know who Rio Tinto are. But really, we look for copper and now lithium and a few other commodities, but copper was pretty much a big focus for the company from an exploration point of view. So I'm not here to represent any of the business units. I'm representing RTX, the exploration arm, and the facts will be from Rio Tinto and the opinions are mine. So I'll just make that very clear so that nothing is treated as though it's official Rio Tinto gospel. Now, when we find something or when we explore things, geochemistry is one of the key tools to work out what's actually there. Everyone kind of knows that. And one of the things we're asked to do very early on is okay, what assay method should we use? Which elements should we have in the suite? What are we trying to do? That's the question I normally ask straight back. I said, what do you need to know? And I guess one of the things that has changed from, say, maybe historic practice into where we are now is that to get an approval for a mine in a country like Australia, you often have to know how to close it before you even built it, right? So it means you actually have to characterise your waste as well as your ore. Anything that is going to be moved somewhere, you need to know what's in it. So one of my little hobby horses is actually a Titanic horse, it's very high, is people still only want to assay what they think is ore. Please stop doing that. I don't care if you're a junior, right? Otherwise, we won't buy you, for starters, if you don't have the right information. So you've got to make sure you're characterising all the material, called ore body knowledge in Rio Tinto, OBK. We love three-letter acronyms, RTX. I work in AAR. We have ore body, OBK, COEs. We've got all that. But really, it's about picking all the things we think will matter from characterising what's in there. What are the geometallurgical characteristics? What are the waste characteristics? Is it going to generate acid when it goes on a dump, and how do you mitigate that? You've got to know all that in advance. So we picked a bunch of data. We collect a lot of spectral data as well. So Osiris is something that we've been using for quite a while on shortwave infrared information. And so when you combine the products that come out of that with a whole bunch of assaying, you end up with a spreadsheet that looks like this. Don't try and read anything into those numbers. They don't mean much. But we routinely have lots and lots of channels of data. And how do you assess the quality? What's important to do the QA/QC on that? And you also need to suddenly do it in a hurry. And you have to sit down with the people involved in the study and go, and at that point we weren't even at the study, and go, well, what are we sampling the right material? Are we doing it consistently? we're getting the right information? Are we storing it in a way that is secure and auditable so that we can show that we're not cooking the books? And how are you checking that? So that's a whole systems thing, not just the assay part. And in exploration, we typically have a small amount of high value data, right? So we tend to, in RTX, it's one of the joys of working in that organisation, is that they listen to their geochemists at least some of the time, and we end up with very high quality data on every sample that we get. But then suddenly you drill something and now you've got to do it at 10, 50 times your current rate, and all your QC systems are designed to handle things where you've only got a hole or two. What changes, what goes wrong? And that's really what today is about. So it can be as simple as core photography and looking, we chucked these things into Imago, I think at the time, and, is someone actually checking to make sure all the core trays are in there? Like, is that a system? Like, who does it, right? It's not something you normally think about. And typically what I've always encouraged my internal or external clients, depending on where I'm working, to do is to have the geologist who drilled the hole be the person that follows everything through. That didn't work here, right? So we ended up changing that. So it's one of the things that do I think that's always the right thing to do? No, but it was an outcome that we experienced here that I thought was quite interesting. So we'll talk about that a little bit and do all the normal stuff. Are you actually walking into the lab? That is not ALS. So just thought I'd say that for Mark. And what are you doing with the pulps and the reject material that you're collecting? How are you storing them? That is also that's an ancient picture from somewhere on a different continent. But the pulps are incredibly valuable, right? And so are the rejects if you store them correctly. Because suddenly if someone down the track actually listens to you and does all body knowledge and is looking at that properly, they might go, you know what, we might need to MET test that thing over there where are all the hot samples, and you don't want to have to go and drill another hole, because permitting a hole is a pain, right? So lots of value there. I'll move on from that little hobby horse as well. So we were running Acquire reports, and our Acquire version at the time is probably always a little bit behind where they're at. So I'm not giving them a hard time or anything, but they were fine for a hole or two. So the geologist responsible for that could look at it and look at every single element we might be interested in, and spend whatever time they wanted validating that. Now we were doing 80 batches a week sometimes, right, when we were going at it, and suddenly there's not enough time in the day to do all that QC in the way that we were doing it. So we had to make some compromises. And what were the ones that we thought were reasonable? And some of this has changed again too, and I'll allude to that a little later, is that exploration have a view about what's important. So we actually shortened the list down to about 7 elements: the commodity elements, path, some potential penalty elements, and ones that we thought might impact, so A and D, right? So we funneled it down to that, and we started reporting some things where we're taking data out of our normal system, and we're using some R scripts that were supplied to us by DataRock, a different name at the time, to help make some charts, to make me happy, because I know what kind of charts I want to look at, and it's very hard to make them in a typical system. And we ran the reports weekly, and they were done by one person. Now, there are significant things that I don't like about having just one person do the QC. They don't know all the rocks that have been drilled. They don't recognise some of the things that you pick up. If you're the guy that did it, and you go, hang on a minute, I logged that kind of rock in there and that's not showing up in here, you miss all that, right? But you have to make a compromise. On the other hand, when one person does it and they've been well trained, you get a lot more consistent outcomes. So one of the things that did change is that the number of failures that we were reporting back to ALS jumped a lot when we had one person doing it. Now, some of those were not genuine failures, so so don't go bash Mark up afterwards. But some of those were around, look, these are concerns, we need to look at them, and we're going to look at a couple of these. So suddenly we were getting a very different view on the quality of our data, because we had a single person who was well trained doing the lot. And like I said, there's pros and cons of that. And some of this was precision related, and I've actually already given the game away on the precision in Dennis's talk around, avoiding the temptation to try and stack the dice, which some people can't avoid when they want to do their field duplicates. and what precision was sensible at which stages of the program. So I don't really want to talk about the precision stuff too much now, except to point out that there are all sorts of QC issues that popped up. We had some brilliant silver assays in the cover for a while, got us very excited, and they were from the drill bit. So there's paint on some of these bits, and the cover there, the Permian sands there are hyper abrasive, and they were just taking the outside off these bits. And it took one of our because we were going, looked at the silver data in there, we're getting very excited. We thought, oh, there's something going on the cover too. Might actually be able to make some money out of that rather than just put it on a dump. But you know, QC people tend to be pessimists a little bit, and we're going, hang on a minute, something not right. And eventually a geologist went out and looked in the tray and went, there's a bit of drill bit in here. So when you've got 20 people logging core and they're all got different experience levels, you don't get very consistent logging, and it was missed in the logging process, right? So QC is a bit of a wicket keeper for some of these things. We talked about standards. I won't do it now. You know, understand where your lab sits in the round robin, but the sizing tests are really important as well. Some really basic stuff. So not all labs give you the sizing data that they have up front. You've got to ask for it. We almost always ask for it. ALS are very patient with us. We also do put a couple of samples through, so it always helps. But when something changes in here, you've got to ask, is there an issue at the lab, which is what this implies? This is not ALS sizing data. That's an example. Is it something going on in the prep facility, or is it actually the hardness of your ore that's changed? Because you might be running your ring mill at the same period of time. So there's never more than one answer. And so the people that go into QC and like it are like the Sherlock Holmes of the geochemistry world. They like finding a little hint of something and then trying and follow it through and work out what goes wrong. And that's why finding the right person to do it is important. Sample weights. We hadn't been using them before, and there's some basic charts that we did in Acquire to make this easier. But we would flag the sample weights and go, hang on a minute, that's a bit large. What happened there? And when we tracked the sample weights too in the RC, we were finding that sometimes they were decreasing with depth far too rapidly, considering that it wasn't that deep a hole. And because we didn't have a geologist on the rig at the time, they were following a few. There was water issues, and they were just losing a lot of sample. So, you know, when you go in a hurry, things go wrong, and you've got to have some way to capture the fact that it has gone wrong, and then what do you do with it? So in the end, some of the RC holes were not used in the resource. They were that bad, right? So we tried to save money by using RC, and it ended up costing us money. Here's an example of a little chart. It was done in Acquire, where we just started plotting the QA sample type as an icon and looking at the weights. And then you can see where you've swapped samples around, and that might have happened in the sample ledger. Or sometimes someone's actually put the wrong thing in the bag. And just a little chart like that, and you can do 80 batches at once, right? You can look across and go, oh, there you go, there's something wrong. Right? Very simple way to speed the whole process up. Doesn't mean you've captured everything, but we tried to capture the things that we felt. How many minutes have I got, by the way? 7. Gee whiz, going all right. You know, you capture the things that you think are going to be most critical to that project. Now, I'm a big believer in, I got trained by Dave Laurie, right? And one of his expressions was, show me the graph, right? So show me the graph, and the right graph, and often that's the role of a geochemist, is to find a way to turn the data, which is a spreadsheet, which is boring as the proverbial to look at, into something that means something, as some sort of graphic. And even just something as simple as plotting a lot of data at once, coloured by whatever it is that you want to do, or a time series chart, allows you to spot changes in your system. It's a process control thing in a way. And you can, by doing a simple chart like the one on the right, you can see where you might, where we've brought new standards in. We've had old standards that have carried along pretty good, but you can see sometimes that the colours don't match exactly where they've gone along that line, and that's where someone's done a sample swap. They've put the wrong standard in the bag, or it's been mislabeled somewhere else. There may be an example in here with XRF data where we follow that trend as well, and you can see where there's a change in instrument, for example. So this is portable stuff that we do use. But it gives you an idea of just a simple chart with more data rather than batch level, which is what we had traditionally got our geologists to focus on. And then every 3 months, someone like me, if I found time, would review all the data at once. That wasn't going to work. We needed to be update more frequently, because if you wait 3 months and you go back to Mark and say, oh, we found a problem that was like 4 months ago, I go, well, sorry, guys, that's a bit late now. And so there's usually a time frame that's reasonable for you to send issues back to the lab. I have had a customer in the part who asked for a resource that waited till the end of the drilling program over 2 years to do all their QC. Right? Yes. And they end up having to reassay most of the deposit, right? Because there was an issue there. So don't do that. That wasn't us, by the way. That was someone else. Another little thing, so, you know, as brilliant as we like to think we are sometimes, one of the geos, who I think now may work as a geochemist for another company, he just came up with the idea in gas of, oh, let's plot the elements that don't really matter for a standard in gas. And lo and behold, a lot of our standards just dropped out. So with different combinations of different elements that no one normally cares about, he could immediately spot all the swaps. So what this meant was even though our failure rate went up with ALS, we were reducing the number of spurious failures a lot more as well. And there were some genuine issues that did pop up. We use a portable XRF. We've twisted the arm of the lab to do this a little bit, where we have a pulp that goes off for assaying, and we also get a PXRF on it to get a poor man's silica and an independent check on the zirconium and the titanium. And you can do all sorts of cool stuff with that, which I can tell you over drinks. But when we track that with time, we could see sometimes when there was a change in the instrument, or it was degrading, or a battery issue. Like, there's all sorts of things, and we would just work with the lab and they would fix it. Right. So we were very happy that these are the sorts of charts. It's just over time stuff where you're using a lot of data. And in the duplicate space, you heard my ethos around using CVs. I didn't win the battle to change to CVs, but we use MPDs. We plot them up. We use MAPDs as well. The MPDs are mean pair difference, so you can see the positive and negative biases, right, between the duplicate pairs, whereas an MAPD allows you to look at the magnitude of the error at different concentration ranges. So we just were able to do that, plot it up. And if you have more data and you plot your batches on top, and you can have all your historic data as a different color in the back, it allows you to see, are things changing or not, right? So none of this is rocket science. It's just around trying to make it easy for people to digest the stuff and do it quickly, because even though that we had a QC person, they only got 1 day a week to do 80 batches, right? And have all the communication. They had a day job the rest of the time. So keep talking to your lab. So one of the things that did go wrong was our gold by fire assay. And there were 2 causes. So there's, which made it really hard to unpick. So 2 minutes. Now we're going to have to really stretch it. So there were 2 issues underlying that. One, there was an issue with some training of some staff at the time, because remember 2019, 2020, things got a bit hard. So there was also a bizarre issue with the CRM. So we'd made our own CRMs, or research made them for us, and they did a good job. They did such a good job because they're very reproducible, but they're also a finer grind size than your typical 75 micron pulverization. And what was happening was that the cup at ALS had some coating on it that particular standard was sticking to, right? And we were losing some of the gold in it, but not the normal samples. So our CRM was failing, but our actual samples were probably going okay. But how do you tell? So we ended up having to do some umpiring just to satisfy ourselves that our actual samples were behaving themselves, and it was actually the standard that was the problem. So that's a good one to show, right? Sometimes you never quite know what's going on. So not only was there a training issue which was resolved, but ALS went and worked in the background. We didn't tell them this. They went and did the work and then came back to us, and we said, well, that's a pretty good explanation. We'll work with that. And then when we changed the cups, we kind of saw that problem went away. So these are all little examples, including plotting density of information. So we might even just put sample weights. Now, what have I got to meet? I've got lab sample weight versus the depth in the hole. And we were finding sometimes we were getting some bizarre results based on the drill hole type. We're getting RC samples plotting where diamond drill hole samples were. We're going, what the hell's going on there, right? So you would never normally do that as part of your typical day-to-day QA/QC. That's an example of a different way of looking at pretty routine data, sample weight data that you're getting at the lab versus other parameters, and things will drop out because you've just got such a volume of information. Really, really handy. And I'm going to have to stop, except to say that part of the QC, which we've not really talked about today, is when people make plots and start looking at patterns that don't make sense. And that's really what these last couple are about. So I will stop there.
Thank you, Mike. Much appreciated. Oscar's talk will be held over till straight after afternoon tea. So we're going to go straight up to the next talk, which is by Tom Carmichael. So completely different topic now. So it'll be really interesting to listen to this presentation. Tom is the Chief Data Scientist at DataRock, whose team focuses on using data science to solve geological problems. His title for the talk today is QC for Machine Learning Applications. Thank you, Tom.
Awesome. Thank you. Thanks very much, Mark. I put a slightly provocative bottom title down there. So most of what I'm going to focus on is the QC part, mainly because there's a lot more intelligent people who've spoken about the QA part today. And so what I'm going to talk about is some of the things that we see a lot of bad QC that happens in the mining and exploration industry around machine learning. We have a bit of a weird niche that we've started to pick up through no fault of our own, which is the idea of when something breaks in a machine learning model, we seem to be the company that gets called. And we then have to do a really interesting audit, which will then identify if we can actually go figure out what went wrong with the model. And so we're going to talk about like 2 or 3 of the more common ones that we tend to see. We'll give everyone dessert before they have to go through their vegetables. The takeaways here are that a geologist is the most important part of any machine learning program. This isn't particularly controversial, I don't think, anymore, but something that is really key here is to make sure that we actually think about what is the problem we're trying to solve. Mike kind of covered it quite nicely, where we were talking about the idea of how do we actually build a system or a machine learning model that solves a particular problem, instead of it being something where we're just going to collect data for the sake of collecting data, build a machine learning model for the sake of building a machine learning model. Machine learning in the geosciences has its individual challenges, and we'll talk a little bit about them. And again, the QC is best done by a geoscientist. I was really happy to see a Simpsons meme because DataRock has a long history of making sure that you have at least one Simpsons meme in any presentation. This is like the slide that we tend to give at the start of any presentation. This graph is actually from a bloke called Drew Conway, who was at the very start of when data science and machine learning was becoming a thing a little bit more prevalently in about 2010. And he was roundly a bit laughed at when he put this graph together. He didn't put geology in there, but he put stats, computer science, and domain knowledge is the thing that he put in there. And he was kind of thought of as being a bit of a Luddite. He was thought of as someone who didn't think that we needed domain expert. We'd actually be able to get away with just the maths and the computer science, that we'd be smart enough that we wouldn't actually need the domain expertise. The Corporate Finance Institute, which we are going to think of as the AIG, but for banking professionals, has basically come out with this statement to go and think about the idea of the application of domain knowledge must be pervasive through the data science process. So when we're doing any machine learning or anything else as well, you're going to need someone there to be holding your hand who actually knows your problem and understands what your issue is. There's some words down here which we're going to explain. Spatial autocorrelation is my very particular hobby horse, and that's what we'll be talking a little bit about today. I won't go through this in any great detail, but this is something that we talk a lot about as a business, but more importantly, this is kind of where the entire industry of machine learning, data science, and all those things are going. It's the idea of we have like these 4 phases that we step through. One of them is a business problem. So we actually need to define what is the geological problem that we actually want to solve here. I kid you not that we used to get asked to just go do AI on geology data. That was the question that we used to get asked. And when we were a much smaller consultancy and we didn't have a choice but to take that work, we used to sometimes take those jobs when perhaps we shouldn't have. But we actually need to come up with a really good question So if we think about this from what this means from a QA, QC perspective, we actually need to think about, does this even make sense to ask our data set? Does this make any sense to actually even think about? And again, we know heaps about limitations about geological data. Everyone here in this room, geochemists, geophysicists, everyone who sits in between, we will know heaps about intrinsically the limitations of our data. If you hand that over to a data scientist, and we'll talk about some spectacularly terrible results that we've been involved with previously, this doesn't come through. This information doesn't come through, and it doesn't get passed through anything that we do. So we have to think about a lot of things that we're doing. It was actually really nice to hear a couple of people have mentioned the idea of like going to see a lab and thinking about communication as well. You kind of need to do that at every level through a data science project as well. You need to be talking to your geoscientist to make sure your problem hasn't actually suddenly shifted on you. You need to be getting buy-in from your domain experts so they're not going to think you're just building a black box model which doesn't do anything. You need to assess how well a model is actually working, and people have this nasty habit of using like accuracy and all these things as well, and people have already kind of had the existential crisis today of how good is good enough. You need to think about a way that you're going to measure that. And then sometimes actually the things that come out of a machine learning project are heuristic rather than algorithmic. You'll be giving something that a geologist can use to solve a problem, but it won't be a machine learning model. It'll actually be something which they can use to be better at their job, but it actually won't be the model itself. It'll be a set of rules that they can apply, or they can update their rules of thumb or their Bayesian priors when they're thinking about their problem. All right, so we'll talk about the thing that normally kills every data science project before you even start, and it's this idea of training, validation, and testing. There's a bit of nomenclature here which we're going to have to learn, but it's not going to hopefully hurt too much. It's the idea of when we build a machine learning model, and we're talking about what's called supervised machine learning here. It's the idea of we have to build a training set, so we have to train our model on something, and then we have to validate it against something else. It doesn't really matter what nomenclature you use here: training, testing, validation, holdout set, whatever you'd like to do. But the thing that you need to do, and the thing that's actually really hard, is this is actually a stupidly difficult problem to get right, because we need to think about what we're doing and what the problem is that we're actually solving. And so how are our labels distributed? How is our features distributed? And how is our data distributed spatially? And this is the thing we're going to talk a little bit about more. All of these things will go blind into a machine learning model whether you want them to or not. And so you have to understand and know what they are. Particularly these first two things, distribution of labels. So labels might be, if we're trying to predict a rock type, it's going to be like, what rock is it? And the features would be, how are we going to predict it? Are we going to predict it with spectra, geochemistry, something in between those things? But the reality is you need to know so much about those things before you start a machine learning project. And the people who are going to know more about that than anyone else are the people who probably collected and then signed up to getting that data. They are going to be the people who know that. And so even before you start thinking about what this looks like, you're going to need to get a domain expert involved. That's not to say that you want them putting their finger on the scale at everywhere through the whole process, but it is something that you want to do to make sure that any of these systems actually make geological sense. So the hill that apparently I've decided that I'm going to die on is spatial autocorrelation, which is the idea of describing systemic spatial variations of a variable. So basically how a numeric variable changes across space. And essentially there's this really, really dumb quote that came from a geographer in the 1960s to describe spatial autocorrelation, which was, things that are right next to each other are more likely to be similar. And that's okay, and you kind of think, thank you for that. But it's not necessarily super useful, but it is actually a really good place to start, because we actually know that our data is incredibly biased. We know that when we're collecting downhole data, we're collecting it really biased in the Z direction. We know that we've got gaps between it, typically in directions in the northing and easting. We know we've got anisotropy in terms of how that variation goes ahead. And if you live in the resource modeling world, this is obviously not something that's even remotely foreign to you, and you're probably thinking about words like kriging and other things as well. But spatial autocorrelation is the actual underlying math and statistics that sits beneath that. So we have to think about the way that we do this. These are the three main things I think that we tend to do. And normally the big one is this top one, which is that we think our machine learning model works. It's this classic thing of someone goes away and does a job and comes back to you and goes and says, we got an accuracy of 90%. And you go and say, again, you have a bit of a crisis and you think, is that good enough? Or what does that actually mean? But it normally just means that you've got a model which you're going to say has worked really well and then will never work again, which is fantastic. You can get a model which works really well on paper. The other idea is it reduces this generalization. So generalization is the mathematical concept of you actually need a model which is not going to just work on your really small training set. It's going to work as you go further and as you get more and more data sets. So we need to generalize our machine learning model, which basically means that we need to learn the signal and decrease the amount of noise that we're going to go get. It's never going to work that way. We're always going to pick up a bit of noise, but we're going to try to do our best to maximize the amount of signal and decrease the amount of noise. The thing that becomes even more frustrating when you go and do these things is you build what's called a black box model. And everyone's probably heard of this nomenclature before, but a black box model is the idea of a machine learning model that you can't see inside of. There is actually no such thing as a black box machine learning model. It's someone not doing their job. A black box machine learning model doesn't actually exist. You can see how they work. You can actually go inside them. If you want to go and get every single neuron out of a deep neural network and then go calculate what it is mathematically, you can. But much more likely, you can go find useful proxies about what the model's doing. But it will give you ideas of like misleading feature importance. So what you thought was driving the machine learning model actually won't be. This is one of the big things that spatial autocorrelation tends to get. It compromises your interpretability, so your ability to actually tell what's going under the hood. And it also becomes just difficult to test whether your model's right. We have had a couple of really spectacular examples of someone not being able to tell if their model even worked internally. And so they didn't know, should we deploy this model? Should we just give it up? What should we be doing with it? The other thing that's like a mathematical construct, which we won't really think about, is that it won't be independently identically distributed. Most machine learning models actually have this as an underlying assumption, and a lot of things that actually spatial sciences have that. And it's the idea that you have all of your data is not biased in how you collect it. And we know our data is going to be biased. So you can do really, really nice, fancy things to go do this. This is the most recent paper I found, which has come up and tried to trademark a name of how to fix this problem. It's called Spatial Plus, which sounds very interesting, and tries to relocate where our sources of error are away from the spatial domain. What's kind of interesting is, and this is probably a really niche fact, is that a lot of the work that's being done on spatial autocorrelation in geography, ecology, and a bunch of other sciences that we tend to steal a lot of our research from are essentially starting to look very, very similar to a lot of the way that we think about anisotropy and variance in the way that we build resource and block models. That is actually, like, we are starting to see a really interesting convergence between those two things. But there are ways to fix this problem. It's not actually unsolvable. It is something that you need to do, mainly because it's going to make your machine learning model worse, which I personally think is always a good thing. But more importantly, it's going to give you a better idea of where it's going to break. Where are the pain points in your model? Where is it going to do well? Where is it going to do really poorly? And so we've done the boring stuff. We can just talk about fun examples now. We can just talk about like some of the things that we've done for some of our clients and different things to show where we've found and identified problems. This is a model that a client had us build where they wanted to go and determine in basically a host rock, a volcanoclastic pile, they wanted to identify when they were getting near a horizon which sat above their ore body. They didn't need to know when they were in ore because it's really easy for them to tell when they're in ore. What they wanted to know is if they were drilling out in the northern or southern leases of their deposit, could they determine when they were getting close and they might have accidentally pulled a drill hole too early? So this is what they wanted to go do. Entirely kind of a sensible thing because they wanted this just to check on top of their geologist so that they knew their geos hadn't accidentally might have picked a hole too early. So what we've got here is we've got on the x-axis, we've got distance to the data points used to create this model, and then the error. So basically the error is essentially in meters, so the ability of the machine learning model to pick it. And then the distance is basically, we built, I think in this case, about 2,500 machine learning models to determine what was the optimum distance that you should build a machine learning model from. How far away for a new drill hole should you be grabbing data? This is in the really, really close brownfields environment. So we do have a lot of data within kind of 200 or 300 meters. Again, there's probably people who do resource modeling who are screaming internally at this to be like, well, duh. But the thing that's really useful here in particular is the idea of there was a really strong spatial anisotropy here as well. So it wasn't just where you should build your machine learning model from in terms of data, it was also orientation. It was also related to geology. So again, this isn't anything new to anyone who's ever like thought about these problems before, but machine learning models don't think about these problems. And we're always kind of think about the idea of like more data is better to feed a machine learning model. Well, actually in this case, less data was considerably better and gave them an infinitely better result. So whenever they drilled a new drill hole, the machine learning model would update itself, only take localized data to then predict how far they thought they were away from this marker horizon. It's not overly complicated as a theory. It is actually quite hard to convey that to someone who doesn't understand geology, to someone who doesn't understand where these things all sit together. But again, it's kind of a nice example of things which we understand intrinsically as geoscientists that need to be put into these things. The last thing, or one of the other things that's really key here, is what is the life cycle of a machine learning model? So a lot of times machine learning models are just built and then they're abandoned or they're left alone. And then what they do is you'll have them running over the top of your database and they'll be spitting back data into a column. And then sometimes they'll drift. And we have very classically had one of these things where a model we built 5 years ago, which we assumed had basically ceased being useful. A client came back to us and went and said, this model's not working anymore. Our company has changed names twice since that client had actually originally come back to us. But we just presumed that they'd stopped using it because they were no longer calling us to give the updates. They'd done the slightly mid-tier junior thing of deciding that it was too expensive to update. So therefore they wouldn't do it, which again, different discussion for a different time. But basically, you have to monitor a machine learning model. You have to monitor the data that's coming in. Mike's kind of covered that, and a few other people have covered that really nicely already. You have to monitor whether the distribution of the data that's coming in is the same as the underlying distribution of the machine learning model. That could change for any number of reasons. Lab method, the lab you're using, you could be going into a new spatial domain, so everything changes. You have to know these kind of things, and you can build these automatically into machine learning models. But you have to monitor their performance and then decide when you're going to trigger a retraining, or most likely, we're just going to go say, we're not going to use that data point. We're not going to retrain the model, but we are absolutely not going to use what the model's using there because the model has given us every indication that it's like, I've never seen this data point before. I am not confident predicting it. And so we have to think about what that might mean and how we might do that. Model retraining, you can decide if you want to go do it. We do have some clients who basically we do the automatic monitoring for them so they don't have to think about it because the less people have to think, the better in the case of some of these things. But what you might do is you might go and say, through time, as we get a decrease in model performance, once we hit a certain threshold, we then just go trigger a retraining. We pick up the phone, we call DataRock, they update it. We also do this for some clients where it just happens in the background and they don't even know. Basically what happens is we just get that data, it keeps getting updated. Once it hits a minimum threshold that we're not happy with, the model just updates. It just updates, it fixes itself for them. You also need to do it if you see a change in underlying data patterns. One of the classic ones that we normally see is that someone will have a satellite deposit that's sitting around out of their main deposit, and they'll love the idea of going and say, what if I just put the data from my satellite deposit into the model, which I know only works at my main one? And you get this chaotic behavior of suddenly we think our model's not working at all, but it turns out they've just gone and chucked something in from 100 kilometers away, and our model actually wasn't general enough to deal with that because we didn't know what they were going to use that model for. You also might change how you're collecting your data. You might start to be more selective with your sampling, and you might just be in a new spatial region. Model drift happens for any number of reasons, but basically there's two types of it. One of them is that your data changes, so your input data changes. This is a quite nice example of something that we saw when basically just the input density of a really important feature for a machine learning model just shifted. When we got back to it, it turns out they'd changed their sampling practices over what they were actually sampling. They were now sampling a different media. And so as a result, the machine learning model stopped working because it's really sensitive to the input data, and that's where it really worked. The other thing is concept drift. So like and this is like, again, this is actually a much harder one to solve for. It's the idea if the relationship between your input data and your label and the thing you're trying to predict changes fundamentally, it becomes really hard to then go do that to deal with that particular problem. But you can actually do these things, right? Like, again, we like to think we're special in geology, but actually we're not when it comes to machine learning models. Everyone has these exact same stupid problems. And so what we want to do is we want to go and say, we're going to detect what data drift is occurring. We can do that statistically. So we've got all these, the tests. So the chi-square test is one of the typical ones we do, but there's a whole bunch of much smarter math that people are putting into open source libraries that you can go do for that. Concept drift is an absolute nightmare, is the polite way to put it, of when that changes, because that becomes really hard to detect because the machine learning model still thinks the same data is coming in, it's still producing the same results, but actually functionally what's happening is the underlying relationship between those two things has changed. Really hard to detect that, but again, it's why we encourage regular QC of our models. We actually don't typically want our clients to go and just rely exclusively on an ML model. We want them actually thinking about what the data that they're putting in and putting in regular QC checks for us. We actually want them giving us data, which is a duplicate, a sample or something else, so that they have confidence in what we're building for them. We want them doing that as well. We want them testing to make sure that we're not missing anything here. Because if we do miss anything, it's incredibly important for us to know. So we'll just talk about like our example of this that we really like, that we really think is quite funny. Machine learning models that people try to build prospectivity across all of Australia. And this is where we'll leave it. There's a couple of extra slides here, but we'll talk about the idea of like, people use this data set to go find new deposits in Australia. For those of you who are familiar with the Australian continent, this data is pretty biased. Also, my favorite part is that Olympic Dam and the Lightning Ridge opal mine are in the same data set. And we go and say, does that make any sense? Does that make even a remote sense of a starting point for our data set? We'd all have a bit of a laugh at that, right? If someone asked us to go do that. But this data set, as far as we can tell, has been handed out 5 or 10 times, and people have been awarded maybe not quite millions of dollars, but quite a lot of money of training machine learning models out of this. And so we need to think about how we can be better than that. There are examples of how you can be better than that, and we won't talk about these in any great detail, but the idea is you actually can incorporate the intelligent way that you think about these geological systems into these ML models. So I'll leave all of those there just because I'm aware I'm running a little bit short of time. But again, actually, the thing that matters, and to bring it round to full circle, is garbage in, garbage out, right? We kind of know this is an analogy that people use, but the importance of data quality is always going to be the highest thing. You need to monitor your models, and you need to have cross-functional teams of people who understand geology, machine learning, and people that sit in the interim. So thank you very much for listening, everyone.
Thank you, Tom. Thank you very much.
Thank you.
So our final presentation for this afternoon session is by Mr. Rob Taub. And Rob's bio was pretty simple. He is passionate about drilling holes in rocks that contain metal, and likes to boast that his core shed is one of the best in the world. Now, he said hemisphere, but I'm saying world. So with that, Rob's talk is a really good case study on QA/QC at the Tuju Bukit Best Practice Mine. Thank you.
Okay. Calling something best practice in a room full of QA/QC practitioners is a dangerous thing to do, but that's what I've done. I'll start my slide with this disclaimer, and my disclaimer here is that most of the work in this is not my own work. I've got a team of fantastic geos, and they've put most of this together. I'm using this mouse. You want to use the mouse? Yeah. So Tuju Bukit is about here, if you can see on this map. Medeka is a relatively new mining company, about a bit more than 10 years old. Tuju Bukit is a pretty good one. It's got about 8 million tonnes of copper and 28 million ounces of gold in the porphyry part. And sitting on top of that, it's got a high sulfidation epithermal, which is making about 100 to 110,000 ounces per year at just over $1,000 an ounce. So it's making a bit of cash. It's pretty cool. Medeka's got a couple of other assets, what I won't talk about here. Zooming in on the geology area, this map's been coloured up by the topo, with the high bits as white and the low bits as blue. And you can see Tuju Bukit sits along here. This is Bali in the middle here, in this belt of rocks, which is full of big porphyry deposits and some famous mines, such as Bad Hijau over here. These have all formed in some sort of a subduction zone context. And if you can imagine one plate going underneath the other one, and then it bubbles up as the magma. Well, about 4 million years ago, those volcanoes were sort of sitting along here. And now they're sitting along here where all these white things are active volcanoes. Just to zoom in a little bit on the area. One thing that the Indonesian government has is the Good Mining Practice Awards. And Tuju Bukit is winning won three of those out of the 5 for last year, for safety, environment and community. And you can see on this slide, here's the mine site here, and that's the processing area there. You can see if I can zoom in on here. We are indeed very close to a community. You can see these little things here, there, little beach umbrellas. This is a surf beach. It's a tourist beach. This is the mine village. That's my house just there. And this is our only place that we're allowed to discharge water in the area. So most mines have a big brown plume coming out from somewhere near where they are. Our only discharge point is on this beach, and it's done so well. It's fantastic. I'm really proud to work there. A quick look at the regional geochemistry. There's this belt of rocks that seem to be anomalous, and you can see these different coloured blobs mean different things based on some different elements there. These things are often associated with porphyries. People who are into geophysics will probably start feeling a bit feel cool here. These same areas that were showing those geochemistry before are now showing these circular bullseye mag things, which people often recognise as sometimes good porphyry targets. This slide's just showing off some fantastic hits. This is our top 20 hits. Some of my favourites are this one, the third one here. So that's 462 metres at 1.3 copper and 1.36 gold. And there's another one a little bit down here somewhere, which is 360 metres at 1.3 and 1.3. Got some fantastic hits there. It really is an incredible place to work. I'll just sort of slide through this stuff pretty quickly. It's sort of just going through the different styles of mineralisation that we have there and the different ore types that go with those. So there's our oxide stuff. There's a bit of transitional stuff. We've got some sort of a high sulfidation copper blanket, which is both hypogene and supergene. And then we've got one part of the porphyry, which has been overprinted with high sulfidation alteration. So that's turned all of our bornite and chalcopyrite into cobalite and enargite and chalcocite. And that's the main money shot there, the porphyry. That's where most of the metal is for this deposit. Okay, let's cut to the chase here. How do we get our QAQC so good? We've had some excellent management support. Medeka kicked off with a lot of, should I say, Newcrest DNA, where our CEO was Col Moorhead, who was the EGM for Newcrest for a long time. And we had a lot of other people who were ex-Newcrest. And ex-Newcrest was pretty good at its QAQC when I was there. I was there for 24 years with Newcrest. So with that management support, we were allowed to build this humongous core shed. We had the funding for the best equipment. We had strong support from matrix matched standards straight off the bat. So we've built 2 batches of matrix matched standards now. We've got to stop saying standards, say CRMs. We've done 2. That's the 5th bundle of mine matrix matched CRMs that I've been involved in making in my career. So I'm good friends with the guys at Aureus who do the best ones on the planet. We've had good funding and continued support from some very expensive consultants. And they've come in and had a look at what we're doing and make sure we're still doing the same thing without drifting off into another dimension. We've got good QAQC practitioners. One of those is myself, and I did pinch another person from Gossawong to join our QAQC team, ex-Newcrest. We were able to implement the best systems and groom our team to be really good at what we do. We document and report everything, and we maintain the standard. And I was mentioning before that well, I was hoping to get a press release out for something new, and this is just sort of by the way. This drill is drilling a hole which is in a new prospect, which was just announced today in a press release. So that's at Guamachin. It's drilling a 500-metre deep hole in a teak forest. That's just an aside. Coming back to the external audits, a couple of key people who've been involved in this place. One of them is Mr. Dominic Francois Bongasson. He is a legend of this sort of stuff, and he helped us pull together the sampling, the sample prep, and make sure our analysis is in tune. He's been on site about 6 times over the last 6 years, or maybe more, and I'm pretty sure people have heard of that guy. Another guy that we've had out there is from AMC. It's Ian Lipton. He's the Earl Grey of grey nomads. He's been on site about 8 times, and he's pushed through and checked almost every single facet of what we do, how we collect the data. He's introduced some really cool tools like Equitip and Whole Tray SG, which is a different way of doing things. I'd never heard of that before. Here's our core shed. So it is a pretty big core shed. The basic workflow is the core comes in at this core delivery area, gets photographed here, and it bubbles its way along through here to get some things done immediately, like Equitip and marking up some stuff. Then it gets dried out, and we do ASD, and then we get it over here and do all these other things that are in this list, and then it goes through some holes in the wall. the core gets cut, comes back out here and gets sampled, and then it comes back into this area for the sample dispatch, and I'm already over time. The best thing about this lab is we've got our own sample prep facility, and you can see we've got Intertech there doing that. And that means we can keep a good watch on everything that happens there. Here's the workflow. People were talking about these before. We've got this stuck up on the wall in all around the place. The key part for this particular thing is that we do small batches of 35 samples with 2 CRMs, 2 coarse dupes, which have come from the Boyd crusher, and 1 coarse blank. So we have small batches so that if we do have any problems there, we're not going to be reassaying hundreds of samples. We're only going to be doing a few. The other key thing is this part. So after it's come out of the LM2, we take, at the rate of 1 in 20, we take a couple of extras. One's we use for an external check, and that goes to a different lab. We have blind resubmissions that go back to that primary lab. We do these in bundles of about 20 for samples that are over 0.2. And we stick in about 5 CRMs in with these with the same CRMs in the same position. So it's an amazing data set to do QA/QC with. And we keep another round as spares. There's a list of how we do everything. So this workflow is stuck on the wall all around the core shed, and make sure people follow things the right direction. I won't go into these kind of things, but that's somewhere, this is an example where someone's done the switcheroo on a coarse blank with a sample, and here's, can't see the assays there, so that's okay. So these are the CRMs that we're using from Aureas, and we take photos of everything we do so that if there's a problem, people can track back and go, oh yeah, I can see that number there, it is, yeah, that's the correct one, and blah, blah, blah. Let's just keep ticking along. There's another bit of the fingerprinting. We know the grades of our things. So if there is something funky going on, you can instantly see, oh, look, the silver on this is 2.7 and it should be below detection. And there's some of those boring charts. On this one, you can see along the bottom here, we've got these dashboards that monitor all of our QA/QC. And I've zoomed in on it here. So we've got the calibration of the Equitip, the MagSus. I'd never even thought about calibrating a MagSus machine until I saw 2 data sets from the same place where the holes were completely different to each other. Thanks to Mr. Lipton for helping us out with that one. Anyway, now I'm going to try and run a video, and I'm going to try and run it really quickly. Let's see how we go here. The video. Got to turn up the sound. It's okay, just let it run, mate. Can you guys hear that? Gentle music, gentle background music.
Whole process in our core processing facility.
All right. This is good fun. The good thing about this is the office. The geology office is in the core shed. So that means
before commencing our work, we always calibrate our tools to ensure they meet our high standards for precision and quality.
This helps us perform our work with accuracy and excellence.
This is the IQ logger calibration process.
I'd never thought about calibrating one of those things before either. So out she goes. She's ready to go and measure some structures. If you haven't used one of these, you should use one of these.
Now, let's move on to the magnetic susceptibility calibration.
Please ensure the MagSys tool is calibrated with the certified calibration block.
Yes, that's right. There's some geologists doing their thing.
For the Equitip calibration, ensure the calibration block is placed on stable ground.
On the cement, because if it's on a soft desk...
Furthermore, we also conduct calibration processes for the caliper, the weight scale, the XRF, and the ASD.
So there you can see our geological models. There's one of the workflows and the core shed. There's the guy who directed this video. His name's Mr.
Next,
Aldaker.
let's start the core shed tour from the core receiving area.
So when the LV parks, when they drop the tailgate, it's at the exact right spot to plop the core straight onto the roller racks, minimising the manual handling.
During the core washing process, ensure the core is thoroughly cleaned of any drilling mud and unrelated foreign materials.
We'll have a new core receiving area in the background there, so we'll be able to do this without getting rain or sun. Core photography, we use a EOS R5, which is a mirrorless camera.
For the core photography, checks that the core information on the tray are complete, then ensure the measuring tape and RGB scale are positioned correctly on the tray before capturing the picture.
It's good to have the hole details or the tray details written on the tray so they're captured in the photos.
Always check the quality of the photos before saving them to the server.
For structure logging, mark the structure and enter the data directly into the database.
He's marking up where to take those IQ logger structural measurements. She's banging away with Equitip.
For the core hardness test, ensure that the probe is perpendicular to the core during data acquisition.
For the XRF data acquisition, this process needs to be performed by certified operators.
We use the same procedure for all core, so whether it's Geotech core, ResDef core or Exploration core, it all gets exactly the same treatment.
Prior to placing the core trays in the oven, make a record of the trays, temperatures, and the time. The temperatures of the oven need to be set to 60 degrees Celsius.
So the reason that we cook the core is so that we can do the whole tray SG and the ASD on the dry core. I should fast forward some of these bits. I've got about 25 geos and there's about 30 people working in the core shed.
The dried core from the oven will go directly to whole tray density measurement. Take pictures of the weighing results for future validation purposes, and ensure that the diameter are measured using the calibrated caliper.
So whole tray SG was introduced by Mr. Lipton. Very cool. Less bias than the immersion method because you can do crumbly, crappy core with this.
After pointing the ASD at the sample, it's crucial for operators to verify the spectrum wavelength results. This ensures the data is free from any interference such as wet samples, spectral anomalies, or low reflectance.
So she's measuring the angles on those predefined points. But she's pretending.
When measuring magnetic susceptibility, ensure the core is lifted to avoid proximity to any metal objects.
See, she didn't look at that. We know that that's just a function. So these two geos are debating the geology. Are we in the bornite zone?
During geotechnical logging, loggers must wear complete personal protective equipment, PPE, to mitigate risks such as splashing rocks or potential hand injuries from hammers.
Some preparation need to be conducted before the Archimedean density measurement, starting from drying the samples in the oven.
Take picture of the sample with its complete identity of the sample. Afterward, measure both the length and the diameter of the sample, weigh the sample, and enter the measurement results into the database.
So the paraffin wax has a much lower melting point, so it's not so hot and crazy and dangerous compared to normal candle wax.
Apply a paraffin coating to the sample.
Coated by paraffin, including underwater weight measurement. Ensure the sample floats freely without touching the bottom of the water.
T measurements conducted, axial and diametral tests.
Point load tests every 5 metres. After it's popped, it gets photographed with its point of failure, and we do more equitips on that to see if we can do some sort of correlation between point load tests and equitips. He's doing
A
barcode.
ticketing procedure is required to mark sample intervals that have previously been determined by the geologists that have.
Let's nip through here. He's marking up a cut line.
The core cutting line is marked at a distance of around 2 cm from the ORI line.
After it's cut, straight through into the soundproof room, or sorry, after it's been marked up.
Before cutting the core, the operators are required to carry out a pre-start inspection guided using a mobile application to ensure that the tool is in good condition for use.
The core cutting process follows the pre-marked core cutting line.
Sampling is conducted by adhering to interval markers identified by pre-attached tickets, and samples are subsequently placed in sample bags.
Geologists need to ensure the correspondence of interval tickets and sample ticket codes on the sample bags.
Chain of custody.
Geologists give the submission form to the laboratory crew. The laboratory crew need to check and verify the completeness of the samples based on the submitted form.
So we weigh them as they are, which is now wet again, and then cook them again.
These for degree chips.
Just through that. Weigh them dry, so we weighed them wet, and we weighed them dry. And then put them in these trays, push them through a jaw crusher. Jaw crusher takes them to 6 mils. We do a size check on the 6 mils. I'll speed that up a little bit. Then into the Boyd crusher. Boyd crusher
Samples from the jaw crusher are crushed again to a size of 2 mm using a Boyd crusher. The splitting sample stage is also carried out in the Boyd crusher.
Once split within the Boyd, they undergo further grinding to achieve a size of 75 microns using a pulverizer.
So we've got 4 LM2s. For some reason for this video, the guys have chosen the one that doesn't have the mill mate that helps you lift the puck out. barren wash between every
Throughout
sample.
each crushing and grinding process, from the jaw crusher to the pulverizer, sieving tests should be conducted on every 15th sample to assess the sample's fineness, ensuring it meets a passing requirement of 95%.
That's the oversize. There's the undersize.
Ensure that the packaging is labeled with the correct sample code and verify it against the dispatch listed analysis.
Blah, blah, blah. Off to Intertech goes. So the Intertech lab is in Jakarta. So these have 2 flights a week from Banyuwangi to Jakarta. Although we're about to build our own on-site fire assay.
Store the remaining samples
and
for
wet lab.
archival purposes. These archived samples serve as a record and are retained for future reference or potential reanalysis as needed.
Before being stored in containers, it is essential to vacuum the sample using nitrogen to ensure optimal preservation of its quality. Vacuuming with nitrogen helps remove any residual air and moisture, which could otherwise degrade the sample over time.
Survey holes in specified holes with known azimuth and dip to ensure accuracy during drilling.
So that's the 10-hole camera thing.
In the final stage, geologists validate and perform QA/QC on all data to ensure the quality and reliability of all data.
That's the end. So this guy's, the vacant area there is about to turn into a fully blown assay lab with ICP-MS, OES, the whole lot. Sorry for going over time, Mark.
Thank you, Rob. We have just gone over a little, but if anyone has any questions for the 3 presenters, they can talk to them during afternoon tea. I'd like you to thank our 3 presenters for a fascinating session.
There's one question for Rob.
Oh, we actually have one question from online. Okay.
Okay.
We'll have one question from the online.
Question from Max Verdugo. For reference, how does the whole tray SG measurement work? What do you do about drills, blocks, core loss, etc.?
Excellent question. So if we think about a whole tray, we know the diameter of the core because the guy's measuring it with that that caliper thing. We know the length of the core because it's measured on the runs. We know the weight of the core tray. We know the weight of the core blocks. All those things get entered into the system and it spits out the SG, whole tray SG. It's quite good. It does, when you do the normal Archimedean method, you usually choose samples that are solid and hard so that they can be dipped in the wax. This method will also accommodate the soft, mushy stuff or the stuff that's growing out, fluffing out of the core tray. As long as you can get the diameter of it, it is a fantastic method. Generally a little bit lighter SG.
We could have a very lengthy conversation about the pros and cons of tray SG measurements or density measurements. But anyway, thank you. Pleased we've actually got some responses from our Zoom online people. So that's it for this session. Please speak to the presenters during afternoon tea. We will be back here exactly at 3:40 for session number 4. So enjoy your afternoon tea and thank you again to our 3 presenters.
Thank you.